Okay, so in the last class probably we have already started discussing about FM bandwidth. So let us just explore a little bit more on FM bandwidth, but before that for our own advantage we would like to give some intuitive understanding of narrowband FM. You remember we have derived this formula that phi FM t, that was actually A cos omega c t when we took the real part of this, minus kf a t sin omega c t minus kf square a square t divided by factorial 2 cos omega c t and up to infinity. Okay. So, now what we have said that initially people started saying that we want to have a very small deviation and that will create a narrowband FM. At that time people were thinking that narrowband FM means it is almost 0 bandwidth. Okay, so that del f will be 0. So, with that understanding we say that kf will be much smaller than 1, okay, very small value of kf. Immediately what happens, all these higher terms actually goes away, square to cube to up to infinity goes away, and the phi FM becomes this. Which is almost like AM, okay. Though we are calling it FM, it almost means the functionalities almost looks like FM, okay. So, we have a carrier term over here which is this, and then we have just AT multiplied by sin omega c t. It was for AM, it was cos omega c t and there was a plus sign, just that difference, otherwise it looks like AM, okay. So, earlier that was our amplitude modulation, right. How on earth this is becoming a frequency modulation? This is something comes to our mind every time we ask this. But remember here also the amplitude variation will be very restricted because the k value is very small, okay. So, A multiplied by this kf into AT, so whatever that AT variation is, it will be very small, okay, it will not be very significant. So, the amplitude variation, as we can see, it will be restricted, okay. And because we have got it from the FM formula, so this will also have corresponding frequency variation. We will later on when we will be drawing FM phasor diagram, probably you will understand this. Right now we are not trying to prove that part, but this faithfully represents that above one, and that was according to us FM signal. So, we know that at least we could prove that this does not have too much of amplitude variation, that is for sure, okay. So, that is something, but there will be some amplitude variation once we start truncating it, that all those higher signal actually they were balancing those amplitude variation. So, once we truncate that, however small, there will be some amplitude variation. We will also see when narrowband FM will be generating, how do we really control that part. So, that is something also we will see, but this is what happens at this instance. If I now talk about, because we were talking about this narrowband FM, we have just demonstrated because we wanted to talk about bandwidth. So, we were talking about bandwidth. So, at this instance, if this is the FM, earlier understanding was narrowband FM must have frequency deviation almost 0. So, the overall bandwidth should be 0, but this is coming out to be narrowband FM. So, what is the bandwidth of this? This has this modulation term. So, it must be having a bandwidth of 2B if B is the bandwidth of that, okay. So, immediately I can see if I just make narrowband FM, that means del f tending towards 0 or very low value of kf, then this particular function tells me the bandwidth of that FM must be 2B. But what was our derived formula? So, beta FM in frequency in f domain, not omega domain, angular frequency domain. So, that was del f plus 4B, right. Now, make del f tends to 0. So, this ad hoc formula tells me this is 4B, but from here direct from FM I can get that this must be 2B. right. So, there is some fallacy in this still, but what I can understand, because this was an ad hoc formula. So, I should not believe in this formula directly. I know that this formula should be almost correct, but I should not completely believe on this formula till I derive some very accurate kind of formula. But with this ad hoc formula I can say that probably the overall bandwidth, because what we are doing, we were wherever the means that sinc function goes to 0, we are taking up to that. So, maybe that is overestimation, because I am almost going towards 0, and then after that all the other ripples will be smaller, and the ripples that are coming from internal sinc, this is just the boundary sinc, internal sinc they will be even smaller. Okay. So, probably we are overestimating it. So, it should be intuitively we can say, because this must be 2b whenever I put del f tends to 0. So, intuitively I can say it must be, this is the upper bound of that. So, it must be something like this. We will come back to this. Okay. So, this must be the FM bandwidth. Okay. Let us try to see how we can deal with that. Okay. So, to deal with that, let us try to define one thing which is called frequency deviation ratio. Okay. It directly comes from that particular formula where we are saying that probably this FM bandwidth should be this del f plus b. Wait a second, was my derivation correct? Del f plus 4b, yes. So, we are saying del f plus 4b, right. Okay. So, this particular deviation I am taking this, sometimes you will see this derivation means this del f, I have taken it from the entire deviation. So, it sometimes taken from 0 how much it varies in the positive half and negative half. So, that way they write also 2 del f. So, accordingly the formula gets modified. Okay. So, if I write that way, then it becomes 2 del f plus 4b. Okay. If the del f definition is not the entire deviation, it is just from the center, that omega c how much in the positive half and how much in the negative half it goes. So, if I just take it that way, so it becomes this, or we can write 2 del f means 2 into del f plus 2b, and we have said that it may be not 4b, it may be 2b. So, with that approximation BFM must be 2 del f plus b. Okay. So, one of these formula will be correct, we do not know. Okay. Right now we have derived this one, but we are saying that probably from narrowband FM this should be the correct one. Okay. Now, whatever it is, the deviation ratio is defined as this. I take this b out, okay. Then I will have this thing del f divided by b plus 1. This particular thing is called, termed as deviation ratio. Okay. This is actually tells us how much deviation I get in frequency divided by what is the bandwidth of the original message signal. Okay. So, that ratio is defined as a term called beta. Okay. In our next derivation probably this beta will be useful. So, this is actually the deviation ratio that we are talking about. So, now let us try to do this. Okay. Suppose I have a message signal which is actually a tone modulated signal, or which is a tone, or which is a single frequency. So, cos omega 8. So, I am not now, this was by the derivation of Carson's, means how he could derive the FM bandwidth. So, we are just going through his derivation. So, here what we are saying, that earlier we are taking any FM. So, any message signal you could take, and then we are trying to derive the whole formula. So, now we are restricting ourselves, we are saying probably we will just test it for a tone modulated signal, and we will do the proper derivation, okay, the proper bandwidth derivation. So, we are saying that a message signal is just a tone or a cosinusoidal at frequency omega m. Okay. So, this is omega m, and of course, omega m must be much smaller than omega c. So, this condition is valid. Okay. So, if this is the message signal, first I have to, for constructing FM, I have to first construct AT. Okay. So, what will be AT? That will be the integration from minus infinity to that particular t value. Now, if I wish to do that, it will be minus infinity to t alpha cos omega m t, sorry, alpha d alpha, or I should not say alpha, that should be some other things. So, let us say it is x dx, okay, because alpha is already there. So, I have taken a dummy variable, I just have to take a dummy variable which is x. So, omega m x dx, okay, omega m x inside this. Now, this integration, if I wish to evaluate, I already know how to evaluate that, but at minus infinity it will create problem for me. So, if I just say that at minus infinity I already know that this particular thing will be, means this AT will be already 0. So, this is something if I know, we are just assuming that at minus infinity we know this. Okay. So, if I just assume that A minus infinity I know that is 0. So, then immediately I can write this as integration of that and putting as t. So, this should be alpha divided by omega m sin omega m. Now, in place of x I will put t, because at minus infinity I know it is 0. So, this is my AT, right. So, now I wish to evaluate the bandwidth of it. So, what I will do, I will first go to the actual FM signal. So, let us do that the way I have done, that psi hat FM t. Let us try to evaluate this part. So, this is actually A e to the power j omega c t, right, plus kf into this AT. So, kf into alpha divided by omega m sin omega m t, right. I can write it this way. Now, I can also write, we have already derived this del omega is actually kf into mp, this is something we have already derived. So, this I can write as alpha into kf, because mp becomes alpha. This is mt, okay. What is the maximum value of this? That is actually alpha, and minimum value minus mp is just minus alpha. So, mp becomes alpha. So, I can write del omega in terms of alpha and kf, right. So, this is something I can write. So, kf into alpha immediately I can write as del omega, okay. So, I can write this as e to the power j omega c t plus kf into alpha I can write as del omega divided by omega m sin omega m t, right. Okay. Now, what is beta? That deviation ratio, that was actually del f, or if I represent it in terms of omega, that should be del omega divided by the bandwidth in omega domain, okay. Now, for this particular message signal, what is the band or bandwidth? It is just a tone at omega m. So, the bandwidth must be that only, right. So, B must be omega m. So, I can write this B as omega m, and del omega is this one. So, del omega by omega m must be my beta. So, beta del omega, and B must be omega m. So, this becomes my beta. So, I can write this as A e to the power j omega c t plus beta sin omega m t, fine. Separate it. Okay. So, that is my phi hat FM. Now, try to see this signal. Because I have a sinusoidal, it is a periodic signal, right, with frequency omega m. or this angular frequency omega m. So, because it is a periodic signal, what can I do? My Fourier series tells me that this can be represented as a Fourier series expansion. Okay, so that understanding tells me that I can write this e to the power j beta sine omega m t as a Fourier series expansion with coefficient dn, and the frequency I know already omega m. So, this must be e to the power j omega m t, and this n varies from minus infinity to plus infinity. Okay. Wait a second, I have not written it correctly. Yeah, that's correct. Okay. So, this must be the case. Okay. So, basically at every omega m I will be getting this term, probably that m I have not written over here. Yes. Okay. So, it must be that every frequency term I will be getting, okay, with respect to this, and yeah, it is not n, it should be n. Yeah. So, for every value of n I will be getting a corresponding n, and I will be getting that frequency term, right. Now, this dn, how do I calculate? So, dn becomes the Fourier integral. So, that should be 1 by 2 pi. So, that is, or 1 by t. So, the period is basically the overall period is omega m, that is in angular frequency. So, it should be omega m by 2 pi, or the time should be 2 pi by omega m. So, it should be minus pi by omega m to plus pi by omega m, and 1 by t means it should be omega m divided by 2 pi, and the integration goes, this is the signal itself, e to the power j beta sine omega m t, right, multiplied by e to the power minus j n omega m t, right. That is the Fourier series analysis dt, right. Now, just put means pi by this t by omega m as x. So, immediately what you will get is this becomes 1 by 2 pi, goes from minus pi to pi, e to the power j beta sine x into the power minus j n x dx. Okay. Or I can write it 1 by 2 pi minus pi to pi e to the power j beta sine x minus n x dx. Okay. This particular integral is not something that can be calculated easily. Okay. That has to be numerically evaluated, but this has a name. This was by Bessel, and this is called Bessel function of means first means this is nth order actually. So, because this n is there, so it is called nth order Bessel function. So, I can write this as this integration 1 by 2 pi integration minus pi to pi e to the power j beta sine x minus n x dx. This can be written as j n beta. Okay. So, this particular integral I can write it as j n b beta, right. So, immediately what happens, my representation that phi f m hat t, what happens to that? This dn can be now represented as this. So, immediately I can represent this whole thing as a summation n goes from minus infinity to plus infinity j n beta, which is that coefficient, and I will have e to the power j omega c t was already there multiplied, and here it should be plus n omega m t, which is coming due to the Fourier representation, okay, Fourier series representation. So, this is something what we see. immediately I should take the real part of it. So, I will be getting this just the cost component of all of these things. So, phi fm t I can write as a summation n equals to minus infinity plus infinity j n beta cosine of omega c t plus n omega m t. So, you can see that it is actually creating, see at omega c I have something and then plus n minus n all infinite terms it is creating. Okay. So, this is something which is happening. So, again we can say probably the overall frequency is infinite. Okay. So, that is something we can immediately from here we can say, because it goes from minus infinity plus infinity, all of them will be populated. But if you carefully analyze this j n beta, it is revealed that as n goes bigger than beta plus 1, the significance of this or the value of j n beta becomes insignificant. So, this is something from the Bessel's function plot for different values of beta and n, you can actually see that. Okay. So, for every n there is a beta plus 1 means beyond which that n value is not really significant. Okay. So, what we have to do, we have to, so for every value of n, the overall significant term we can actually evaluate. Okay. So, what we can say, the significant sideband should be up to beta plus 1, because n, this value of n for a particular beta value, that beta value is defined already, right. So, beta value is coming from the FM modulation, del f I have given and the bandwidth of this one. So, once I provide a beta value, I know n becoming beyond beta plus 1, that is becoming insignificant. So, basically what happens to my bandwidth? The overall bandwidth becomes from omega c I take beta plus 1 on this side and beta plus 1 on this side, that must be the overall bandwidth. Okay. So, I can immediately write that my FM bandwidth for this tone modulation must be 2 beta plus 1. Okay. So, this is something I can immediately write. So, this happens to be my overall FM bandwidth, but this is just a number, I still have not really accounted for bandwidth. Each one of those numbers I take, so this many numbers of frequency I will be taking. What is the separation between them? That is actually either omega m in omega domain or fm in frequency domain or f domain. So, if I really wish to call this a bandwidth, I need to multiply this with fm, because that many terms I am taking. So, how many overall this thing I will be taking? That should be this multiplied by fm. Okay. This fm, okay, or I can write that as omega m divided by 2 pi, right. So, if you start writing that way, you will see that if I just write it, so suppose let us keep it as fm. So, I multiply this, so this becomes 2. Now, this beta earlier we have represented with respect to the omega. Okay. So, beta is just a ratio, either I do it with respect to omega or b, it will be just 2 pi gets cancelled. So, I can even write beta with respect to del f and corresponding fm. So, I can write that as del f divided by fm plus 1 into fm, right. I can write this way. Immediately what do I get? Del f plus fm. This is the famous Carson's theorem. Okay. So, immediately you can see for tone modulation, the overall bandwidth of fm is nothing but 2 into that del f, which we have defined as frequency deviation due to the FM modulation itself, plus the bandwidth. of the message signal. Here it was tone modulated, so FM becomes the bandwidth of it. Okay. What he could do is to prove this only, that for a tone modulated signal this will be happening, and we have seen that for a generalized modulated system probably this will be del f plus, here it should be means overall 4b. So, it must be taken as 2b inside. Okay. But what we have seen also that narrowband FM tells me that this should be plus b. So, that is why this formula was more accepted. There was no formal proof of this because it is very difficult for any other things. So, there was no formal proof of FM bandwidth overall, but people could understand that this must be this. Okay. So, that is why finally they could take the overall FM bandwidth was 2 into del f plus this b, and there was the other formula where it was 2 into del f plus 2b. Okay. So, one of them is acceptable, this was more acceptable because it came from the tone modulation, that is first thing where we did proper bandwidth calculation, and second thing is this actually for the narrowband FM this defines the correct bandwidth. Okay, where this formula does not define it correctly, it gives me 4b, which is not true for narrowband FM when del f tends to 0. Okay. So, that is why historically this bandwidth definition was more widely accepted, and then we could see all kinds of relationship with respect to this. If my del f becomes much bigger than b, then the thing that people were actually saying that the frequency deviation should be the FM bandwidth, that actually happens where del f is already that frequency, it is not the narrowband part, it is the wider band part, where you have a huge deviation, that means the kf value is already big, you have a huge deviation. On top of that, the bandwidth that is coming from this particular thing, the actual message signal bandwidth, that will be insignificant. So, there I can say this BFM is nothing but 2 into the deviation, okay, as long as the deviation is taken from omega c to plus half or minus half, whichever, not the whole deviation, then it will be just del f. Okay. So, that is something we have already told. So, all the understandings were correct, but in some perspective. Okay. People thought that it is infinite bandwidth, yes it is infinite bandwidth, but some of the part of that bandwidth becomes insignificant, okay, which we have seen through the Bessel's function proof also for tone modulation, that Bessel function itself whenever you take your n greater than that beta plus 1, that becomes insignificant. Okay. That is numerically seen. Okay. So, that has been observed, or you could also see that from the perspective of our derivation, that we have taken sampled values and then try to derive it. There also we could see that means no, not that part, actually expanding that FM and then getting all those a square, a cube, a to the power n term, and then n tends to infinity, that becomes convolution of all those at, that also takes it to infinity. So, infinite bandwidth conjecture was correct, there is no doubt about it. But the thing is that some of the things are insignificant, that is also something we have proven, that this a to the power n kf divided by factorial n actually goes to 0. And then we could also see that it is not del f, because it is del f if the bandwidth is already, that del f variation is already sufficiently large. Initially people thought that it should be del f, which is true if it is already wider band FM, that means it already covers a huge amount of bandwidth, then we can say it is just del f. Okay. But initially what people thought, with that logic that it is del f, they could actually make the del f very small, and they were thinking that it should be just del f, but that was wrong, because del f is always supplemented with a b term, and if del f goes to 0, that 2b at least will be there. So, whatever happens, that 2b factor will be there. So, it will never be, that is what we wanted to prove, that it will never be anything better than double sideband. It will at least be worse than that, whatever it is. So, bandwidth wise, what we can prove now, FM is probably not as inefficient as people were thinking, that it covers the entire band up to infinity. So, it is not as inefficient as that, but it is much inefficient in terms of spectral usage compared to any other FM counterpart, AM counterpart. So, this is something we have clear understanding now. So, that is where after this bandwidth calculation and all those things, means the reputation of FM got dented. Initially people started jumping into FM because they thought this is bandwidth efficient, but that got dented because of this derivation. So, now we have seen that probably FM is not as good. What we will try to do in the next few classes, we will try to prove why FM is still good in terms of noise cancellation, interference cancellation and channel non-linearity. So, all the impairments that comes from channel. Okay. So, thank you.